Semigroups and their representations, Lecture 10, Problem Session. Problem 1. Prove that a regular subsemigroup of an inverse semigroup is itself inverse. Solution. Let S be an inverse semigroup, and let T be a regular subsemigroup of S. Then every idempotent of T is of course an idempotent of S. That is, the set of all idempotents of T is a subset of the set of all idempotents of S. Since S is an inverse semigroup, the idempotents of S form a commutative subsemigroup of S, so the idempotents of S commute. Since the idempotents of T are a subset of these, the idempotents of T commute as well. And so T is a regular semigroup in which idempotents commute, and this means that it is an inverse semigroup. And this completes the solution. Problem 2. Consider the symmetric inverse semigroup ISN. Let ION be the set of all order-preserving elements of ISN. That is, all elements alpha in ISN such that the inequality that x is smaller than y implies the inequality that alpha of x is smaller than alpha of y for all elements x and y in the domain of alpha. A. Prove that ION is an inverse subsemigroup of ISN. B. Compute the cardinality of ION. C. Determine Green's relations for ION. D. Prove that ION is an H cross-section of ISN, in the sense that each H class of ISN contains a unique element from ION. And E. Prove that an element of ION is nilpotent if and only if it doesn't have fixed points. Solution. Let alpha and beta be two elements of ION, and x and y be two elements in the domain of beta, such that beta of x and beta of y belong to the domain of alpha. If x is smaller than y, then beta of x is smaller than beta of y, because beta is assumed to be an element in ION, so it preserves the order. But then, alpha of beta of x is smaller than alpha of beta of y, because alpha is an element in ION, so it also preserves the order. This means that the composition of alpha after beta is an element of ION because it preserves the order. If x is smaller than y, then alpha after beta of x is smaller than alpha after beta of y. And this means exactly that ION is a subsemigroup of ISN. Also, for any alpha in ION, the element alpha is the unique order-preserving bijection from the domain of alpha to the codomain of alpha. And then the inverse element alpha inverse, that's an element which exists in ISN, then also the unique order-preserving bijection from the codomain of alpha to the domain of alpha. And this means that alpha inverse belongs to ION. And this implies that ION is a regular semigroup. Each element has at least one inverse. But then ION is an inverse semigroup by problem 1 because it's a regular subsemigroup of an inverse semigroup. And this proves part A. Now, to compute the cardinality of ION, let us construct an element alpha in ION of rank k. And this k can be 0, 1, 2, and all the way up to n. So to construct such an element, we can choose the domain of alpha in n choose k different ways. We can also choose the codomain of alpha in n choose k different ways. And if we have such domain and codomain, then there is a unique order-preserving bijection from the domain to the codomain. So this means, using the multiplication rule, that the number of elements in ION of rank k is equal to n choose k squared. And now if we add up over all possible k's, we get that the cardinality of ION is equal to the sum over all k from 0 to n choose k squared. And this completes part B. To determine Green's relations for ION, Let us first note that since ION is a subsemigroup of ISN, then Green's relations for ION are subsets of the corresponding relations for ISN. So indeed, if we have that alpha and beta are R-related in ION, this means that alpha is equal to beta after gamma, and beta is equal to alpha after delta for some delta and gamma in ION. This should be alpha. And this, of course, implies that alpha and beta are R-related in ISN. Similarly for the relations L and J, but then the relations H and D follow, because H is just the intersection of L and R, and D is equal to J. We are talking about a finite semigroup. So we only need to look in the opposite direction. So let alpha and beta be two elements in ION that are left related in ISN. So we will eventually prove that they are also left related in ION, and so the left relation for ION is just the restriction of the left relation for ISN. So since alpha and beta are left related in ISN, they have the same domain. Let gamma be an element in ION, which is a unique order-preserving bijection from the codomain of alpha to the codomain of beta. But then, directly by construction, gamma after alpha is equal to beta, because gamma after alpha has the same domain as alpha and the same codomain as beta. And there is only a unique element in ION which goes from the domain of alpha to the codomain of beta. But domain of alpha is the same as the domain of beta, so this element must be equal to beta. So beta is the unique element in ION with such domain and such codomain. So this means exactly that alpha and beta are left related in ION. So two elements alpha and beta in ION are left related if and only if they have the same domain, and if and only if they are left related in ISN. Applying the anti-involution which sends an element alpha to its inverse, we obtain that two elements alpha and beta in ION are right-related if and only if they have the same codomain, and if and only if they are right-related in ISN. As a consequence, two elements of ION are H-related if and only if they have the same domain and the same codomain, and if and only if they are H-related in ISN. Also, as we already mentioned, ION is a finite semigroup, so we know that D is equal to J. So it's enough to determine the relation J, D is then automatic. Let alpha and beta be two elements in ION, which are J-related in ISN. Then these two elements have the same rank. Let gamma be the unique order-preserving bijection from the codomain of alpha to the codomain of beta. That's an element in ION. Let delta be the unique order-preserving bijection from the domain of beta to the domain of alpha. This should be domain. Again, delta is an element of ION. And similarly to the case of the relation L, we have that beta is equal to gamma after alpha after delta. So delta maps domain of beta to the domain of alpha, alpha maps domain of alpha to the codomain of alpha, and gamma maps codomain of alpha to the codomain of beta. And this means exactly that alpha and beta are J-related in ION. And so two elements in ION are J-related, if and only if they are D-related, if and only if they have the same rank, if and only if they are J-related in ISN, if and only if they are D-related in ISN. And this completes part C. Now about H cross-section. An H-class in ISN is uniquely determined by the common domain of all elements in this class, let's call this domain X, and the common codomain of all elements in this class, let's call this codomain Y. Let us note that the cardinality of X and Y are the same because any element of ISN is a bijection from the domain to the codomain, and that common number is the rank of this element. So given these X and Y, there is a unique element of ION with domain X and codomain Y, and this is of course given by the unique order-preserving map from X to Y. So in other words, every H-class of ISN contains exactly one element of ION. And this is exactly what was necessary to prove for part B. So it remains to solve part E about nilpotent elements. So we need to prove that an element of ION is nilpotent if and only if it doesn't have fixed points. So it's clear, of course, that a nilpotent element cannot have fixed points, because if you have a fixed point, it remains a fixed point in any power, so you will never reach zero. On the other hand, let alpha in ION be an element without fixed points. Consider all possible powers of alpha, it's a finite subsemigroup of ION, and then it must contain an idempotent, because any finite semigroup contains an idempotent. Let's call this idempotent eta. So if eta is 0, then alpha is nilpotent, and we are done. If eta is not 0, then eta has a fixed point. Let's call this point A. Let R be a minimal positive integer greater than 1, such that alpha to the power Ra is equal to A. Alpha, by our assumption, has no fixed points, so alpha of A cannot be equal to A. So we can fix R minimal greater than 1, such that alpha to the power R of A is equal to A. Consider the points AI defined as alpha to the power I of A, where I is 0, 1, 2, and so on, R minus 1. All these points are different by our assumption. Now let us look at points A0 and A1. We know that they are different because R is greater than 1. So we either have that A0 is smaller than A1 or A1 is smaller than A0. So we consider the first case, and the second case is similar. Applying alpha, alpha belongs to ION, so it preserves the order. And alpha moves A0 to A1 and A1 to A2. So A1 is smaller than A2, because alpha preserves the order. Applying alpha once again, we get that A2 is smaller than A3, and so on, and we eventually get that AR-1 is smaller than AR, which is A0. But this implies that A0 is smaller than A0, and that's a contradiction. And this completes part E. Problem 3. For I, an integer between 1 and n, let us set n underlined I. We define it as the set n underlined, that's a set of all integers between 1 and n, minus I. So now for an integer I between 1 and n minus 1, let sigma I denote the unique element of ION, whose domain is an underlined sub I, and whose codomain is an underlined sub I plus 1. And let sigma n be the unique element of ION, whose domain is an underlined sub n, and codomain is an underlined sub 1. So now the problem is to show that the element sigma 1, sigma 2, and so on, sigma n, is a monoid generating system for ION. Solution. For an integer I, let us define sigma I in such a way that sigma I is equal to sigma j if I and j are equivalent modulo n. And similarly, we define an underlined sub I. So that will be easier for argument to assume that our index for both sigma and n underlined, that these indices belong to z modulo nz. For any rank I between 0 and n, let us denote by d sub I the set of all elements in ION of rank I. Let us note that dn is the singleton consisting just of the identity. There is a unique order-preserving map from an underline to itself, and that's the identity map. And also all sigma I, by construction, they belong to d sub n minus 1, because the domain of each sigma I contains n minus 1 elements. We have n underlined, and we throw away one element from there. Now, by construction, for each I, the codomain of sigma of I is equal to the domain of sigma I plus 1. Consequently, for all j greater than or equal to I, the composition of sigma j after sigma j minus 1 after and so on after sigma I, we will denote it by sigma j comma I. This belongs to Dn minus 1, because in this composition the codomain always matches the domain of the next element. Let us note that the domain of sigma j, I is equal to n underlined sub I, and the codomain of sigma j, I is equal to n underlined sub j plus 1. Therefore, Dn minus 1 is the set of all sigma ji if we let j and I be arbitrary integers, because any element in Dn minus 1 is uniquely determined by its domain and codomain, and the domain and codomain can be some n underlined and then sub some I. Denote by m the submonoid of ION, which is generated by sigma i's. So we have just proved that this monoid contains both Dn, because Dn is the identity, and Dn minus 1, because all elements in Dn minus 1 are compositions of our sigmas. So it remains to prove by induction, so we will prove by induction, that if M contains some dk, then it also contains dk minus 1, if k is smaller than n. So let alpha be an element in ION of rank k minus 1, which is smaller than n minus 1. Fix some I and j such that domain of alpha belongs to n underlined sub I, and the codomain of alpha belongs to n underlined sub j. So such I and j of course exist because the rank of alpha is not n, it's strictly smaller. But then of course alpha is equal to the idempotent epsilon with the index n underlined sub j after alpha after the idempotent epsilon with the index n underlined sub I. Recall that epsilon sub x is the identity on x. Let gamma be the unique element of Dn minus 1 with domain n underlined sub n and codomain n underlined sub I. Then epsilon with the index n underlined sub I can be written as gamma after gamma inverse. Let delta be the unique element of Dn minus 1 with domain n underlined sub j and codomain n underlined sub n. Then epsilon n underlined sub j can be written as delta inverse after delta. And so we can now write alpha as delta inverse after delta after alpha after gamma inverse. So we want to prove that alpha belongs to M. Of course, delta, delta inverse, gamma, gamma inverse, they belong to M because they belong to Dn minus 1, which is a part of M, as we already know. So it is enough to prove that the element beta, which is defined as delta after alpha after gamma, belongs to M. By construction, the element n doesn't belong to the domain of beta, and the element n doesn't belong to the codomain of beta. Consider now the element beta prime, which is obtained from beta by extending it by the identity map from n to n. So beta prime has domain, the domain of beta union with n, and the codomain of beta union with n. On the domain of beta, beta prime is equal to beta, and finally it sends n to n. We just trivially extend beta to this beta prime. Then beta prime has rank k, because we added one more element to the domain, and hence by induction it belongs to M. Also, the element beta is equal to epsilon with the index n underlined n after beta prime after epsilon with the index n underlined n. And this implies that beta belongs to M, and so M is equal to the whole semigroup ION. And this completes problem 3. Problem 4. For each positive integer n, consider the set Dn minus 1 in ION and define R sub n as Dn minus 1 union with 0. For two elements alpha and beta in R sub n, set alpha star beta to be equal to alpha after beta if alpha beta and alpha after beta belong to Dn minus 1 and 0 otherwise. A. Prove that Rn with this operation star is a semigroup with 0, 0. B. prove that this semigroup is isomorphic to the semigroup Tn, which is given by the following presentation. It has generators 0 and ai, where I is an element in Z modulo nz, and the relations are ai plus n minus 1, and so on, all the way down to ai is equal to ai for all I, and ai_aj is equal to 0 times aj is equal to aj times 0 is equal to 0 times 0 and is equal to 0 for all I which are not equal to j plus 1. Solution. Consider first the set A, which we define as ion minus dn. So we throw away the identity from ion. And the set B, which is obtained by throwing from A all elements of rank n minus 1. So A consists of all elements of ion of rank at most n minus 1, and B consists of all elements of A of rank at most n minus 2. Since we cannot increase the rank when we compose partial maps, both A and B are ideals of ion, and we can consider the risk quotient of A modulo B. And then, of course, we have the obvious bijection between Rn and A modulo B. This bijection is the identity on Dn-1, and it maps 0 to B. And from the definitions, we see that this bijection is actually a homomorphism of semigroups, and this completes part A. So the semigroup Rn is actually the risk quotient of A modulo B, where A is the ideal of ion, consisting of all non-invertible elements, and B is the ideal in A, consisting of all elements of rank at most n minus 2. To prove part B, let us note that the defining relations imply that 0 is a zero element of Tn. So if we look at our defining relation, 0 is an idempotent, and multiplying with all generators we get 0. So 0 is by definition the zero element in Tn. Next, let us note that directly from the definitions, if we look at ion, then the product of sigma I after sigma j has rank n-1 if and only if I is equal to j plus 1 modulo n. So if and only if the domain of sigma I coincides with the codomain of sigma j. So in other words, sigma I after sigma j is 0 in the risk quotient if and only if I is equal to j plus 1 modulo n. Also, the element sigma I followed by sigma I plus 1 followed by and so on followed by sigma n plus I is the unique element of ion whose domain is n underlined sub I, and the codomain is n underlined sub I plus 1. And since such element in ion is unique, this must be equal to sigma I, which has this domain and this codomain. And together this means exactly that sigma i's satisfy the defining relations of the semigroup Tn. Therefore, mapping ai to sigma I induces a homomorphism from Tn to A modulo B. And this homomorphism is surjective, since we know that all sigma i's generate this risk quotient. So they generate A, and so they generate also the risk quotient. So it remains to prove that the cardinality of Tn is at most the cardinality of A modulo B, which is n squared plus 1. So from the defining relations, we have that the word in our generators aj is non-zero only if it has the form ai on the right, followed by ai plus 1, followed by ai plus 2, and so on for some I. Also, if such a word has lengths n plus 1 or more, we can use the defining relation to make it shorter. Here is the defining relation which makes such increasing word shorter if its length is n plus 1. Therefore, Tn has at most n square non-zero elements, because we can choose I in exactly n different ways, and then the length of the word which starts with I in at most n different ways, so it can have lengths at most n. And so the cardinality of Tn is at most n square non-zero elements plus 1, 0. That's exactly n square plus 1. and that the cardinality of A modulo B. And this implies part B. Some problems and questions at the end. Problem question 1. Prove that a regular semigroup is a group if and only if it has a unique idempotent. Problem question 2. Prove that the set Xn of all elements alpha in ISN such that alpha of I is less than or equal to I for all I in the domain of alpha is a sub-semigroup of ISN and determine its cardinality. Problem question 3. Determine the minimal inverse subsemigroup of ISN that contains this Xn. Problem question 4. Describe principal left, right, and two-sided ideals of ION. And problem question 5. Determine the defining relations of ION with respect to the generators sigma i's. Thank you very much and see you next time.